All right, welcome back. Here's what we're going to do today. Oh, just as a quick reminder, whenever we have an in-class assessment, it does not cover stuff from recently, right? So like an in-class assessment on Thursday, like an exam, only covers up to last Thursday. Same thing with quizzes, right? If we have a quiz on a Tuesday, it only covers up to what we did in class last Tuesday. The idea behind that, I know it can be a little weird to like cover something in class and have a different thing to be tested on, but it gives you time to come in and, right? Like so the thing is, nothing that we do this week is on tomorrow's test. Oh, there's a test tomorrow? Okay, sorry, I have my announcements out of order. I'm just, all right. Yeah, so the point is don't tune out completely, right? And I should be very clear about what I'm saying. Nothing new that we have done is on the test. All along, though, we are using things that are older techniques, and so you'll see that again today. All right, but nothing that we do that's truly new will show up on the test. Basically, after class last Thursday, that's when I write the test, just so you make sure. All right? Okay, so we're good. Today, and then next time, I guess next Monday, we are going to look at some equations, some quadratic equations. Here's the punchline of what we're looking at. Some quadratic equations don't look quadratic, but after one or two steps, then they become very familiar territory. One comment that will apply a little later in class today is this. It is okay to square both sides of an equation. In fact, we've done this once or twice, squaring both sides of an equation. However, there's like one little extra thing, a caveat to worry about. And so far we've squared both sides in very controlled situations. Nothing bad has come from this. But now we have to be careful. So be sure. So that'll make sense a little bit later. Not in our first example, but I just needed to mention this. Take a look at this example. We're going to solve the following equation. It has fractions in it. So 2 over. One way to solve an equation that has fractions in it, I want to remind you of our old technique. Strategy is you can compute the LCD off to the side. The fractions isn't here. So there's an x in the denominator, there's an x minus. There are no common factors, right? This x isn't a factor. So the LCD is just the product. So it is this thing, namely x times x minus 3, that I'd like to multiply on both sides. And here's how I'll do it. Let me write the original, let me leave a little space, but then I'll write the original left side. So the original left side in parentheses here, 2 over. Same deal on the right side, leave a little space, and then the original right side of 3 in parentheses, so I'll just have x. The original left side, the original right side are in parentheses, and just to the left in each case. I'd like to distribute on the left side. So just treating this entire x times x minus 3 as a block. I'd like to distribute that to the first fraction and to the second fraction. You could very well distribute x to just the x and the 3, but that'll create actually more work. You'll have to FOIL later. So I'm going to, as a block, this whole thing x times x minus 3 is the a in the distributive law, a times b plus c. Times x minus 3 will distribute to the first fraction. So what I mean, and let me show the steps here, because there's some confusion that occurs. So I won't skip steps. I have x minus 3 times the first fraction, 2 over x minus 3. And I distribute again this x times x minus 3 times the second fraction, 2 over. Okay, what happened here? I distributed the x times x minus 3. So there's one copy over here, one copied after the block. Okay. On the right side, you know what? I know that I have time over there, so let me take this slow here too. I've got x times x minus 3 times 3. There are these three things being multiplied together. I can juggle the order of multiplication, and I'll just write 3x times x minus 3, and I'll distribute the 3x in there. Over here, this x minus 3 is a factor in the numerator that cancels with this x minus 3 factor in the denominator, right? This denominator is really x minus 3 in parentheses times a 1. So the x minus 3's cancel, and you're left with 2x. In last class I had somebody just say x, so like, what about that 2, right? Oh yeah, right. So it's 2x, see this plus sign here. And then this x, which is a factor in the numerator, and that x factor in the denominator cancel. You're left with 2 times the quantity x minus 3. On the right side, distribute the 3x, and you'll have 3x squared minus 9x. Already at this point, I feel very good about this equation. It still looks a little freaky. It's not as bad as what we started with. But what I like about this 2x plus 2 times quantity x minus 3 equals 3x squared minus 9x is that I already see what we have as a quadratic. Right? The highest power of x is going to be 2, even if we distribute over here, which we are about to do. But the highest power of x is a quadratic. And I say this because I want you to notice that right away. Now the point is we'll have 2x. Okay, we're going to distribute the 2, so we actually have another 2x. And then we have minus 6, right? So 2 times negative 3 is negative 6. Common error is just to write a 3 here. Looking better as a quadratic, let me add the 2x's together, and I'll have the two 2x's. So 4x minus 6, 3x squared. Do the following, I guess subtract 4x on both sides, and have negative 6 to 3x squared minus 9x, oh sorry, well, negative 9x minus 4x. Let me just rewrite that line right up here. Okay, I'm just going to rewrite. I don't have to do this, but I don't have as many lines. I'm about to write down another line here, which is mathematically correct, but I'm going to erase it right away because I'll talk about why it didn't work out for us. What I'd like to do is leave the quadratic and linear term on the right side, so add 6 to both sides. 0 equals 3x plus 6. I'm about to erase this line, though. The reason I'm going to erase it, it works, it's fine, but I'm going to erase it because it turns out that we had factoring, then we could zero product property. It's not going to work out. So since we don't have factoring, if you have like this, we would complete the square, and the first step would be to get rid of the constant, right? We'd subtract 6 on both sides, and that's what the previous line looks like. So there, we've gotten rid of the constant. In completing the square, what's the next thing to take care of? Yeah, we got to divide by. So we want to make sure that the coefficient in front of x squared is 1. So divide by 3 on both sides. Divide on the left side, and you'll have negative 2. Divide by 3, and you distribute that 1/3, if you will, to both terms. So you have x squared minus 13 over 3. X over 3, but I really like. All right, what's the linear coefficient? Negative 13 over 3. And then the second stick, right, because we're going to divide by 2, or 2 in the denominator. The constant, then, is we've got to take this negative 13 over 6 and we've got to square it. So negative times negative is positive. You'll have 169 over 36. That is the number, and is the number we add to both sides. So let me take the previous equation here. I'm going to add 169 over 36, then minus 2. So I wrote the fraction first. You could have written negative 2 plus the fraction, but I wrote this order, so I have less. So sorry that I added 169 over 36 on each side on sort of separate sides of the equation, but I did really take the previous line, and what's different is there's a plus 169. I like dealing with this side. I mean, normally this is on the left side normally, but whatever. This side is, in my opinion, the easier side to deal with, because this should factor as x something quantity squared. Okay, so the second stick, not the linear coefficient. So x minus 13 over 6. Picture, draw the square if you need to. Over here, we did some work on this side. On the left side, let's also do something here. This is 169 over 36 minus 2 over 1. We need a common denominator, 72 over 36. I'm not ready to deal with the right side yet, so let me just rewrite quantity x minus 13 over 6. But on this side, since I have the same denominator, I can subtract fractions, right? You have one of these little Caesar's pizzas that's been cut into 36 pieces, and you eat 169 of them, and then you throw up 72 of them, right? How many did you really eat? So you ate 97 of them. Okay, and I did engineer this problem carefully. This is one I made to make sure that this 97 is. So we'll square root both sides now. 97 over 36, but we're square rooting. And we square root on the right side as well, so the square and the square root cancel. We're left with x minus 6. But I have an error in my work, plus or minus sign. I can put the plus or minus sign on the right side. That's very typical for us. If you do, because of the two terms, you need parentheses. We'll just put the plus or minus sign on the other side. It's sort of easier to deal with the plus or minus sign on the side that does not have the variable. I'm running out of room again, so let me just rewrite this plus or minus. Here's the thing. I'm not going to mess with the right side right now, just x minus 13 over 6. But on the right side, I copied down the plus or minus. Remember, the root of a fraction, you can just root the top and bottom separately. So I've got root 97 over, I'm not going to write root 36, I'm just going to write 6. And now, to solve for x, I just need to add 13 sixths on both sides, right? So I'll have x on the right side equals, on the left side, I'll have 13 plus or minus root. So I added 13 sixths on both sides and then also, that look all right? All right, so today the story is to just try a couple different types of problems that, we'll apply our quadratic techniques or some other techniques that are related. Okay, we're just going to see some new strategies. I'd like to solve the following equation. Solve x cubed minus 3x squared minus 2x plus 6 equals 0. This is weird. First of all, I really celebrated back in the previous problem when we were at this point where we had 3x squared and the highest power of x was, now look here. Oh shit, it's cubed. Okay, but there are 4 terms here. There was another setting way long ago when we looked at 4 terms. Anybody recall there was a strategy involving 4 terms? Factor by grouping. In the past, we did factor by grouping way before we even dealt with equations. We were dealing with expressions. That is the thing that's like one side of an equation. Well, let's try factor by grouping here and see if this works out. Factor by grouping, just to recall, you look at the first 2 terms, ignore the last 2 terms momentarily. Does something factor out of x cubed and out of 3x squared? X squared. X squared times the quantity, so x squared times something is x cubed, minus, and then x squared times something is 3x squared. Out of the next two terms, we'll also factor. I'd like to factor out a negative 2. So I'll have negative 2 times the quantity x minus 3. We didn't do anything to both sides, so the right side remains a 0. Just to make sure, this is a place where there's common confusion. It really is x minus 3 in parentheses. Think about it. You distribute a negative 2 to positive x to get negative 2x. You distribute a negative 2 to a negative 3 to get a positive 6. We're going to keep doing the factor by grouping process, so we're not going to change the right side at all. The punchline is the right side will just remain a 0. So I already wrote equals 0. Now take a look. Both of the terms are separated by plus or minus signs. There's two terms here separated by this minus sign right in front of the 2. Both terms have an x minus 3. So that x minus 3 should be written outside the new set of parentheses. So there's this new set of parentheses in front. And what goes in here are the other factors. So you've got x squared minus 2. So you've got x squared minus 2 quantity times. This is the completion of the factor by grouping. And if you're unsure, you're just like, wait, is there another x minus 3 factor here? Just check by foiling this, you should get x cubed. Does that look all right so far? Now what? Well, take a look. We've got this thing times that thing equals 0. Zero product property, we can set each of these equal to 0, right? So we have a 0 product. Things are multiplied together. So we can set the first factor equal to 0, x squared minus 2 equals 0, or x minus 3 equals 0. You can, I'm not requiring you to write this on a quiz or test ever, but for right now, if you want a reminder of what's going on in your notes, you might just write ZPP. So take a look at this equation. This is a quadratic equation that does not have the linear term. There's no like plus 3x here or something. So when there's no linear term, there's this old strategy, get the quadratic on one side and the constant on the other. Add 2 to both sides. X squared equals 2. Square root both sides. X is equal to plus or minus root 2. Let me copy down the or. And then here, this one's not bad. Just add 3 to both sides, so x equals 3. This is a little imbalance, so I'm just going to write x is equal to 3. So there's actually 3 solutions. Root 2, negative root 2, and then the third solution is 3. We're using an old strategy in a new setting in equations. I might as well just repeat the strategy that we said, but you see 4 terms. 4 terms, consider factoring by grouping. It might not work, but it's worth a shot. Now, so we're doing this in an equation now. Okay. All right, we'll try something else. Today's a day of seeing all these things that we've seen kind of put together in different ways. So let's solve this equation. This looks a little freaky. Solve the equation x to the 5 halves equals x to the 1 half. We'll talk about the strategy right after. I want to do the example first. So this first step is not going to make a lot of sense. You'll say, okay, I agree we can do that, but why did we do that? So let me just try this, and then we'll see what happens. I'd like to subtract x to the 1 half on both sides, and I'll have x to the 5 halves minus x to the 1 half equals 0. Okay, there's already a 0 on one side. Now here's what I'd like to do. Both of the terms, this sounds a little funny, but I'd like to factor out, if I can, in x to the 1 half. So let me just get the shape of all this set up. The right side's not going to change. I already wrote the equals 0. On the left side, x to the 1 half and a set of parentheses. Here's my question for you all. X to the 1 half times something equals x to the 5 halves. Let me just point out that way back here, I asked the same question when you thought maybe it was ridiculous for me to ask. X squared times something equaled x cubed, and you all answered x. X to the 1 half times something equals x to the 5 halves. To the 5th, so the thing is, if you have x to the 5th here, it's not x to the 5th. Here's what happens. So if you would distribute x to the 1 half to x to the 5th, we're multiplying things with the same base. When you multiply things with the same base, you have to add the exponent. Right? So now the question becomes, so that it'll be x to the something, but it won't be to the 5th. The question becomes, what exponent do you need here so that when you have x to the 1 half times x to the whatever is equal to x to the 4 halves? I like that answer, right? 4 halves. Okay. We'll pause here. I'll drop the pen. Make sure we're okay with this. Right? So we're factoring out x to the 1 half. So x to the 1 half times x to the 4 halves. Let me point out this. There's a lot going on here. What's going on is we're talking about the distributive law. We're talking about when you multiply things with the same base, you add the exponents. These exponents both happen to be fractions. Good thing they have the same denominator. Because when you add fractions with the same denominator, you just add the numerators. So I actually really like hearing 4 halves here. So 1 half plus 4 halves is 5 halves. Is 4 halves 2? Of course it is. And we'll simplify that in the next step. But I think this is good to have here. It's like there's so much going on. I like this 1 half plus 1 over 2 plus 4 over 2 is 5. Next thing here, after the minus sign, x to the 1 half times something is x to the 1 half? 1. It is common for people to forget when you're factoring when you have a 1 or a minus 1 in parentheses. Okay, let's write this the following way. X to the 1 half times x to the 2 to simplify the 4 over 2 equals 1. So now look, I have 0 and I have a product. I don't care that this factor is not in parentheses. I still have something times something. So I can use the 0 product property to have x to the 1/2 power equals 0 or x squared minus 1 equals 0. Let me remind you that when you have a 1/2 power, that's the same thing as a second root or a square root. So I rewrote x to the 1/2 as root x. Root x equals 0. And guess what? Square both sides here to undo the square root, and you have x is equal to 0 squared. In other words, x is equal to 0. Over here, x squared minus 1 equals 0. We can do the same thing as we did right here. Right? Like you have a quadratic term, constant term. We could add 1 to both sides just to try something a little different. Can't I factor x squared minus 1? And I'll have x plus 1, x minus 1 equals 0. Check by FOILing. And now I'll have x plus 1 equals 0, x minus 1 equals 0, that's x equals -1, or x is equal to 1. And you know what? I'm just going to copy these ors down here, and they're all nicely vertically aligned. So there's actually 3 solutions, x equals 0. Second to third step. We factored out an x to the 1/2. So x to the 1/2, so I wrote the x to the 1/2 outside parentheses. This is just like what happened here. Factored out an x squared. It's just 2 is easier to deal with than 1/2. And so we had to, so how do we fill in what's here and here? We had to answer the question, x to the 1/2 times what is x to the 5? And in that process, we use other things, like when you multiply things with the same base, you add the exponent. And since the exponent is a fraction, to add fractions, you have to have the same denominator. Oh, yeah. If you had a 1/3 here, then you'd have to answer the question, like 1/3 plus which fraction? I shouldn't even use an x. 1/3 plus which fraction is equal to 5/2, right? You could solve for y. And so you have y is equal to 5/2 minus 1/3, and then so really off to the side, I like get a common denominator. So this can be done to find out what the exponent. You'll usually end up seeing the same denominator here, so it'll be kind of clear what you want to do. This is getting like I appreciate the question, but this is getting into what if territory that we won't even. There's 1 or 2 things I want to say about this. You write down some warnings. In general, avoid dividing both sides by a variable or any expression. So why not? Why avoid this? You might accidentally divide by 0. So the point is, it's generally speaking not a good idea to divide both sides by x. The variable is called x. Don't divide both sides by x, because x could very well be 0. In fact, if I point out what happens in this problem, we do actually have x equals 0, and it's very tempting at the very beginning here, when you have x to the 5/2 equals x to the 1/2. It's very tempting to divide both sides by x to the 1/2. That's dividing by the variable, dividing by something that has a variable. If you end up doing that, you actually will just get this equation, x squared minus 1 equals 0. And you get these 2 solutions. So in hindsight, x is allowed to be 0, and you would actually miss one of the 3 solutions by doing it. So generally speaking, yeah, divide by whatever you want, but you want to. All right. The thing is, instead of dividing by the variable on both sides, what you should do just as an alternate approach is factor. And so instead of dividing by x to the 1/2, how would you factor? That's why I subtracted x to the 1/2 on both sides. Right? How would you factor those 2 things on 2 different sides? Okay, that will take some getting used to, and we'll see some other examples of this next Monday. But I want to try. There's a certain type of problem that really pieces together a lot of things we've seen. So there's a strategy. We'll do 2 examples of this. So if you have an equation. If an equation has a radical containing a variable, then isolate one term with a radical on one side. Then square. Or in some other problem, maybe you have to cube. Typically square both sides. In another problem, it might be cube both sides. Here's the thing though, the comment at the very beginning of class was when you square both sides, you might get extra solutions. So doing this, when you square both sides, this may create false, extraneous. So check your answer. Here's the thing, you can always check your answer for solving equations anyway. Good too if you have extra time on a quiz or test. But in the setting of these, then you really have to check. You might get false solutions. You got to discount those. So let's take a look at an example. Here's an example problem where the strategy applies. Solve the equation 1 plus root equals. So first off, does the strategy apply? Let me point out this. if an equation, we have an equation because of the equal sign, has a radical, there's a radical, and then the radical should contain the variable in it. So you notice inside it says 7 minus 5x. I'm looking at that x and saying, this fits the strategy. Now what the strategy says is isolate one term. This sounds a little funny because we only have one term with a radical, but we'll see the next example. So get the term that has the radical on one side by itself. Well look, we've got this radical term right here, but there's this plus 1, this other term as well. So let's not have this plus 1 here. Subtract 1 on both sides. The answer step is subtract 1 on both sides and we'll have root 7 minus 5x equals 9 minus 1, in other words 8. Once you have the radical on one side, comma, then, so only after, then square both sides. So we'll square both sides. You square the left side and the square root originally there and the square we're about to introduce, cancel each other out. You're left with 7 minus 5x, just the stuff that was inside the root. On the other side, we also square, and we'll get, let me subtract 7 on both sides, and you'll have negative 5x is equal to 64 minus 7 is 57. And then finally, divide both sides by negative 5. X is equal to negative 57.5. That minus sign can hang out in the numerator, or in the denominator, or just off to the side of the math. You only have one math. Do the steps look all right here? Okay. The one thing we have to do is, because we did the squaring both sides, we have to check the not. So we'll check if x is equal to negative 57 over 5 is a solution. How do we check? All we do is we take this number and we plug it in for the x on the left side and on the right side and see what happens. So on the left side, this really, by the way, digs into what it meant to solve an equation. It wasn't just about isolating x. It's about, do you have the list of numbers and all the numbers that make the left side equal to the right side? So the left side is originally 1 plus root 7 minus 5x. I'm just going to plug in x equals negative 57 over 5. So 1 plus root minus 5 times, and then for the x I'm going to plug in negative 57 over 5. Now this, you might think, looks awful to do without a calculator. These are not. These are actually not so bad without a calculator if you pay attention to the steps that you can use. So I've got 1 plus. You have a 5 in the numerator and a 5 in the denominator. They cancel out. Right? 5 in the numerator, 5 in the denominator. They cancel out because we're multiplying. So what you're left with is minus negative 57. In other words, plus 57, right? If you insist on doing the 5 times 57 first, then yeah, you pay more of a mess. But you can see the 5's cancel, so do that instead. And this is 1 plus root 7 plus 57. So 1 plus 8 equals 9. Right? On the right side, let's see what the right side is, because we have to take the right side and plug in, for every x, we have to plug in negative 57 over 5. So the right side is 9. Oh, those are equal. Yes. Okay, so this is the solution. So because we have 9 on the left and the right side when you plug in negative 57 over 5, so we end up getting that x equals negative 57 over 5 is the only solution. So we had to check. So maybe you want another example. We'll try another one. I'd like to solve this equation. So solve root 2x plus 1, then minus 1 outside the root sign equals root x plus 4. Before we get going, let me just point out some things that cannot be done. You cannot distribute this root. Not with a plus sign here. You cannot distribute and write root x plus root 4 or root x plus 2 or something like that. The root does not distribute. Same thing over here. This root doesn't distribute. Also, this plus 1 here and that minus 1 don't cancel each other out. That's a plus 1 inside the root symbol. This is like 2x plus 1. What number do you square to get 2x plus 1? This minus 1 does not participate. However, the strategy applies. The strategy says, if you have an equation, we've got that. There's an equal sign. That has a radical. That has a radical. We've got 2. And we better just make sure that one or the other radical has the variable inside it. Actually, both of these do. Right? Just the variable here and the variable there. So then, what's the strategy tell us to do is to isolate one of the terms with a radical on one side. So either we need this root 2x plus 1 on a side by itself, or we need this root x plus 4 on a side by itself. What do you pick? Root x plus 4 on a side by itself. And why? Because it's already on a side by itself. Good. We got one term with a radical on one side by itself. We square both sides. I want to take this in stages. To square the left side, I'm just going to write the original left side in parentheses, and then put a square. On the right side, when you square though, on the right side when you square, the square root originally there and the square cancel out, so you're left with x plus 4. So I want to take things in stages. So I know this looks a little different, but on the right side, because we squared both sides, the square and the square root cancel. On the left side, when you square both sides, when you square the left side, it's that entire left side that's going to be squared. By the way, the square here does not distribute. Does not distribute because of this minus sign. So I had the question last section, wait, if we're squaring both sides, don't you just get rid of that square root? I say no, because it's this root this minus 1. That minus 1 is screwing things up here. Whole thing that's going to be squared. And so we don't have any formula that we have that deals with taking the square and distributing it, not when you have a plus or a minus sign. So instead, we're just going to write down what squaring means. Exponentiation is repeated multiplication. So the left side, the right side will still be x plus 4. But the left side is minus 1 outside the root, and then write that again. Root 2x plus 1 minus 1. We have no formula that really deals with this, so instead, we're going to use the meaning of exponentiation and now FOIL this out. It's the only thing we can do. We don't have a formula that applies. So, when we FOIL, the firsts are multiplied together. Root 2x plus 1 times root 2x plus 1 is 2x plus 1. And then when we multiply the outside, the O in FOIL, we've got root 2x plus 1 times negative 1, so that'll be negative. When we multiply the inside, it says a negative 1 times root 2x plus 1, that's minus root 2x plus 1. And then we have negative 1 times negative 1, that's positive 1. The right side hasn't changed, it's still just x plus 4. So we haven't done anything to both sides except in the first step. First step, we squared both sides, and all we've been doing is now rewriting the left side. Let's clean this up a little further. I'd like to collect my terms. Over here, the 1 plus 1 combined, so you have 2x plus 2 to combine the 1 plus 1, and then we can combine these negative root 2x plus 1s as a minus 2 root. The right side still remains in x plus 1. This equation is still freaky, and it's in part strange because you still have this root here. But look, the strategy applies again. We have an equation that has a radical containing a variable. Equation, check, radical with a variable inside. Isolate this term. We want this term on one side by itself. I think it'll be a little convenient, actually, to not have the minus sign in front. So let me get this term on the right side. So I'm going to add 2 root 2x to both sides. So my new right side is going to be 2 root 2x plus 1. I want to isolate the term, this term here, on this side alone. So this x and the 4, which are on the right side, should no longer be here. I'd like to then subtract x on both sides and subtract 4 on both sides. So don't I have 2x minus 2x minus x is x, and then I have 2, I have to deal with that 4. Do I write plus 6 here? I don't think, right? Because it's 2 minus a 4, we subtracted 4. How's that look so far? So we've got the term that has a radical on one side, square both sides. So we've got x minus 2 quantities squared, and then on this side as well, we've got 2 times root 2x plus 1 of these squared. So I didn't do any simplification. I just thought I'd write down this. Here's the thing. On the left side, you have x minus 2 times x minus 2. So you FOIL that out. You get x squared minus 4x plus 4. That's what happens when you FOIL x minus 2 times x minus 2. On the right side, we actually have, I don't want to call it distributing, but let me write down somewhere up to the side here. We had this old formula that a times b to the n equals a to the n to b to the n. I'd like to use this. So the exponent 2 applies to a, in this case 2, applies to b, which is this root. So we'll have, on the right side, we have 2 squared. Does that look okay? Right? This is an application of this formula. You know what, I'm going to leave this side alone for now. X squared minus 4x plus 4. Check this out on the right side. 2 squared is 4. The square root and the square cancel each other out. So we're left with 2x plus 1. You know, that should really be in parentheses. And now, so the left side stays the same. X squared minus 4x plus 4. The right side distribute the 4. You have 8x plus 4. Oh, good. It's actually this step, even the step before, I saw we had a quadratic. And it's the highest power of x is 2. Right? So it was a big mess to get there, but we have a quadratic in there. So ultimately, if we had to, we could square. But let's get all the terms on one side and see what happens. X squared Subtract 8x on both sides, so minus 12x. You have to subtract 4 on both sides as well. Actually, there's a plus 4 on both sides, so when you subtract 4 on both sides, you just don't write the plus 4s anymore. So you actually just get x squared minus 12x equals 0. Hope that looks okay. Now we can, if you'd like to, complete the square, but we don't need to. Whenever you have the quadratic and the linear term, you can complete the square, you'll get the right answer. But instead, you can just factor out an x and have x times, in parentheses, x minus 12. Look, I just factored out an x. Check by distributing. X squared minus 12x. So look, we've got a 0 on one side, and we have a product. That x does not have to be in parentheses for this to mean it's x times x minus 12. So we set each factor equal to 0. X equals 0, or x minus 12 equals 0. So x equals 0, or x is equal to 12. Those appear to be our two solutions. Yeah, well, in fact, we're going to do this right now. So there's like one setting, test or not, love work or not, whenever. There's one setting in which you really have to check this. Not bad to check your answers if you have time. But here, you might end up creating false solutions. So when doing this, by this I mean squaring both sides, you can create false solutions, so we have to check. So we're about to do that. Is x equals 0 a solution or not? I'm going to try to organize the word. Is x equals 0 a solution without the original left side? 1, then a minus 1 outside parentheses. That's the original left side. Let me write down the original right side on the next one. The original right side is root x plus 4. So what we're going to do is check by plugging in 0 for x and see if the left side is the same as the right side. So we got root 2 times 0 plus 1 all in the radical, then a minus 1 outside the radical. We got, oh yeah, so it's just root 1, right? Root 1 minus 1. So in other words, 1 minus 1, which is 0. The left side gave us the number 0. The right side, plug in 0, and we have root 0 for the x plus 4. And we have root 4, which is 2. The left and the right side didn't give us the same number. Equals 0 is actually not a solution. The left and the right side are not equal. We didn't get a solution. We got a false solution. This really is, this checking is not only to make sure that you don't want to declare x equals 0 a solution. We actually want to conclude that x equals 0 is not a solution. But this really gets back to what it meant to solve an equation. If your idea of solving an equation is isolating x, you'd say you're done. But the real idea with solving an equation is to provide a list of all numbers that make the original left and right sides equal, and the original left and right side are not equal. We should check the other one, because this doesn't automatically make 12 a solution. So is x equals 12 a solution? It's possible for the answer to be no. So the only thing to do is just to check. Write down the original left side and the original right side. I already wrote them here, so let me just copy it here. The left side was root 2x plus 1 minus 1. Okay, same deal. We're going to just plug in 12 for each minus a 1 outside the radical. So isn't that root 25 minus 1? Or 5 minus 1, which is 4. And then on the right side, we've got root, we're plugging in still 12 for x, 16, which is 4. Aha! The left and right sides are equal. So we do have a solution. So x equals 12. There's other examples I can't make them up off the top of my head, where you actually can get no solutions at all. So you do have to check. The comment I'd like to make is it's very tempting to say that x equals 4 is a solution. And I'm going to cross this out because it's not true. 4 is just a number that you get on the left and the right side. So it's plugging in 12 for each x that makes the original left side equal in value to the original right side. And equal in value, that value happens to be 4. But that doesn't make 4 a solution. 12 is the solution. While you think of a question, this is an involved question. I get it, right? But it's really just using that strategy alongside just otherwise things that we had seen. The only thing to be careful in this strategy is when you square both sides, you've got to check. Did anybody not get a card on the way in? So here's the drill for the day. Okay? We're gonna we've seen lots of techniques. I know there's just a smattering of techniques. I'd like you to practice. Cube root x squared minus 1 equals 2. X to the 3 halves is equal to x to the 1 half. 3 plus root 3x plus 1 is x. Maybe you have time. That's 2. plus 2x squared. These all look a little different. We've seen sort of similar problems throughout the day. What I'd like you to do is find your group. The card will give you the group, not by suit. So by the number on the card, find your group. This does require moving around. Write these down. Try the same problem together. If you get stuck, ask each other. You do have to move around. There should be exactly 4 people per group. Somebody has to move. It'll be good for you. It'll sit all the time. So try solving these equations, any of them in any order. I just try to mix things up. At least one equation we did today addresses each one of these in one way or another. Just to point out here, if you take this first one, you have the root isolated. Squaring both sides won't get you anywhere. You got to try something else. Don't square both sides. That's not going to get rid of a cube root. You got to do something else on both sides.